This is problem 44 for Model 1. The driver of a car traveling at 16 meters per second suddenly sees a truck that has entered from a side street and blocks the car's path. The car's maximum magnitude acceleration while braking, notice here they point out this is the magnitude, which means that they're not giving you the sign. So the absolute value of the acceleration is 6 meters per second squared. And the driver has a reaction time of 0.75 seconds. The reaction time is the time between first seeing the truck and pressing the brake. The driver stops just in time to avoid an accident. So if they didn't mention anything about the reaction time, you would only have two events. That would be when the car begins to slow down and when the car reaches rest. Because they give us three events, we're going to include the reaction time. So remember that we have to have constant acceleration between each set of events. So the first thing that happens is the driver sees the truck. So I guess because it's supposed to be one instant in time, you might want to say first sees the truck. Event 2 is pressing the brake. So after a delay of 0.75 seconds, the driver presses the brake. And then the driver stops just in time to avoid an accident. So we're going to say reaches rest. So not at rest, but reaches rest. And then if time 1 is 0, event 2 happens at 0.75 seconds. And there's other things that they give us in the table or in the problem. So let's go back and read them and put them in the table. So the car is initially going at 16 meters per second. 16 meters per second. And between seeing the truck and pressing the brake, we should have constant velocity. So acceleration is 0 because the brake hasn't been pressed yet, which means velocity 2 is also 16 meters per second. And let's start at position 1 being 0. Okay, so then the car's maximum magnitude acceleration while braking is 6 meters per second square. Now, based on my velocity being positive, I've already chosen a positive direction. If the car is slowing down, acceleration must be in the negative direction. And we end at rest, so velocity 3 is 0. Okay, now I think that I put down everything that I know from the problem statement, but from looking at the slope and the area of the velocity versus time graph, I can find two things between each two set of events. So I can find position 2 from looking at the slope and the area going from event 1 to event 2, and I can find two things from going from event 2 to event 3. So if I only have 3 unknowns in my table, I should be good. Now I'm going to draw the motion diagram. I said that the car starts at 0 and is going in the positive direction. Initially, the speed is constant. Now I might get into trouble here if I make my arrows too long. So let me think about this. I can do 1, 2, 3, 4, 1, 2, 3, 4. This is event 1. This is event 2. The acceleration between event 1 and event 2 is 0. And then we slow down and we end at rest. So that would be 1, 2, 3, 1. We end at rest and acceleration would be going this way. When I draw the motion diagram, I'm not worried about doing the scale correctly. So the time between event 1 and event 2 is probably much shorter than the time between event 2 and event 3. But if I have 2 arrows between event 1 and 2 and 2 arrows between event 2 and 3, that means the time interval between the 2 pairs of events are the same. But I'm not going to be concerned about that. I just want to show it's a constant velocity and then it's slowing down. So that's all I need from my motion diagram. Okay, then let's go back to my instructions here. I chose my events. I did the motion diagram. Now I do the velocity versus time graph. Now, this velocity versus time graph is going to be a little different than the ones that we saw earlier because we have 3 events. So I'm going to start when time is equal to 0. This is time in seconds. This is 0. This is 0.75, and then sometime later, I don't know how much later, I'll just call that T3. This is velocity in meters per second. We start off at 16 meters per second. At event 2, we're still at 16 meters per second. Drawing your graph, you can do it like connect the dots. So at time 0, I start at 16, and at 0.75, I'm still at 16. So you can put those 2 points on and just connect them there. Then at time 3, I'm at 0, so do a point for that, and then connect the dots, and that is our graph. Okay, now I'm going to break it up into 2 different regions. When I go from event 1 to event 2, I'm going to look at the slope and the area. The area is the change in position between event 1 and event 2. This is actually going to be pretty easy because it's a rectangle, and also I'm supposed to look at the slope and the area between each pair of events, but in this case, looking at the slope isn't going to give me anything to put in my table because I already said that the acceleration was 0, which means velocity 2 is 16 meters per second. Okay, so if I didn't recognize that, then the slope would tell me what that one of those were. Okay, so the slope isn't going to do anything in this case because I already know this is 0 and this is 16 meters per second, so I'm just going to look at the area now. And I have a rectangle. The area is the change in position. For a rectangle, the area is the base times the height, so this is 16 meters per second for the height times 0.75 seconds for the base, and that gives me 12 meters for the change in position. Since R1 is equal to 0, I'll write this out because we haven't done this before. So delta R12 is R2 minus R1, and if R1 is equal to 0, that's just R2. So 12 meters is R2. Okay, also, I want to be clear here. This is going from event 1 to event 2. Okay, and now I'm going to go from event 2 to event 3. And I got to look at the slope and the area. You can do it in any order you want, and it's worked out fine for the problems we've had so far. But depending on what you look at first, you might end up with 2 unknowns in your equation, and then you'll have to look at the other equation before you can figure out what things are. So in order to avoid that, if I have the acceleration here and I have my initial and final velocity, I know more about the slope than I do about the area. So I'm going to start off looking at the slope. And the slope is the acceleration between event 2 and event 3. That's negative 6 meters per second squared. Change in velocity is 0 minus 16 meters per second. And change in time is my unknown T3 minus 0.75 seconds. Or if you wanted to, you could write this as the change in velocity in the numerator, that's just negative 16 meters per second. And if you want to just call this delta T23 and solve for delta T23, and then when you're done, add the 0.75 seconds to it to get T3, you could do that also. Okay, so I have, if I multiply both sides by T3 minus 0.75 seconds and divide both sides by negative 6 meters per second squared, I get this, which is 2.67 seconds. And this is delta T23. Let me do this also. This is delta T23. So you could solve for it like that. Now it's delta T23. So to find T3, I have to add 0.75 seconds to both sides. So delta T23 is T3 minus T2. If delta T23 is 2.67 seconds, then T3 is equal to 0.75 seconds plus 2.67 seconds, which is 3.4 2.42 seconds, and that goes up here. Okay, and you can see if this was 1.75 seconds instead of 0.75, and I rounded it to two significant figures when I put it in the table here, then the 3.42 that I got would be a little off if this had been rounded to something else. Okay, so I did T3 from the slope. Now I do the area. Going from 2 to 3, that's a triangle. The area is, I'm going to call it delta R 2, 3. And a triangle, the area is 1/2, the base. Now here again, you could say for the base, from here to here, this is delta T 2, 3. So you could call it delta T 2, 3, or you can call it T3 minus 0.75, but actually we can do even better than that. I know now this is 2.67 seconds for delta T 2, 3, so let's just put in the 2.67 seconds. So that's the base here. And the height is 16 meters per second. Wonderful. Okay, so that gives me 21.36. But this doesn't go in my table because this is delta R 2, 3. And what goes in my table is R3, which is delta R 2, 3. Delta R 2, 3 is R3 minus R2. So R3 is delta R 2, 3 plus R2. So that's 21.36, which I don't want to round yet because first I want to add the 12 meters to it. And then after doing that, I can round. And that would round to 33.4 meters, or you could just call it 33. I forgot to box things here, so I can box this. Anything that goes in my table, I can box. Okay, and the 33.4 goes in my table here. Okay, and then I have done the motion diagram, correctly chosen my events, completely filled out my table, did the velocity versus time graph, and I'm done with problem 44. But before I move on, I want to talk about something. So I haven't really been using equations in this problem. I've been looking at the slope and the area instead. They give you equations in the beginning of this section, which you can feel free to use if you want to. So one equation that we have on page 8 is the acceleration is equal to the change in velocity of the change in time. So that is the same as looking at the slope for the velocity versus time graph. Okay, so as long as we look at the slope, you can even, we kind of did, right? Use that equation when we look at the slope. So you can do that equation instead. And then they have the equation, one equation for the velocity here, but that's really just the average velocity. And for the change in position, okay, on page 14, they give you another equation here. So here's your two equations. You can use these because they're in the book, but I'm going to be using the slope and the area instead. This one, if you rewrite it and bring the velocity over to this side and then divide by t2 minus t1, that is just the slope. The acceleration is equal to the change in velocity over the change in time. So using this equation, whoops, why did I do? That's 1, 2, and that's 1, 2. Okay, so this equation is equivalent to doing the slope. This equation is equivalent to doing the area, but it's not as obvious. Okay, so I'm going to show that to you when we get to the end of the section. Okay, so if you want to use this equation, you can, but as long as you look at the slope and the area, you don't have to use these equations, and we will talk about that more later.